representation. Here the current is moving from VDD, then you have a PMOS, so VDD to Vout. When your gate of your PMOS transistor, which is represented like this with a bubble here, the current basically moves from VDD to your Vout. When the gate input voltage is at 0 and in that state your NMOS is in the cutoff state. So whenever your PMOS gate voltage is close to 0, the PMOS transistor conducts while your NMOS transistor is in the cutoff state. So whatever is at VDD, it goes to Vout. So there is a direct connection between your VDD and your Vout because the transistor is in the conducting state. So there is a load capacitor and it gets charged up. Now when you switch the input voltage to gates of transistor M2 and M1, where M2 is a PMOS and N1 is a NMOS, then if you give a value 1, which is high value, to the gate, then your PMOS transistor stops conducting while your NMOS transistor is in the conducting state. Means it conducts current. So the current now moves from the charge capacitor C load at the output to the source of the NMOS transistor. So this transistor is in, so M1 transistor, which is NMOS transistor, is in the conducting state, while M2 transistor, which is the PMOS transistor, is in the non-conducting state or is in the cutoff state. So PMOS, when the value is at the gate is 0, PMOS is in conducting state, and when the value at gate M2 is 1, it is the PMOS is in the non-conducting state. Is that clear? Is that clear? Hello?
Yes, sir.
Right. So you should also remember that whenever we are talking about gate voltage, definitely it should be having voltage higher than the threshold voltage. And remember, the operation of the CMOS is actually happening in the enhancement mode and not in the depletion mode. So for all future purpose, we shall be considering the enhancement mode of the MOSFET transistor. So basic operation of a inverter is here. Any questions? Hello? Any questions? If you understand this, it will be easier for you to understand and design any circuits. What do you mean by any circuits? That basically means that you can design any combinational circuit or any sequential circuit, which may be expressed in the form of Boolean expression. So, by the way, I have a question. Why do we use Boolean expression? Why do we use Boolean expression? Hello?
To use minimum number of CMOS these CMOS circuit inverters.
Yeah, you're right. Actually, the whole idea is to reduce. So whenever you have a large expression and when you solve the Boolean expression, what you get, the expression gets reduced. So the reduced expression would be requiring lesser number of transistors. When we are talking about transistor, we mean and PMOS and NMOS transistor to implement that expression. So before the expression is solved, you would require more number of transistors to get the same output. And once you solve the Boolean expression, you would require far lesser number of the transistor, so your output would be the same. The output never changes. The output never changes. So for the same output, you would be reducing the number of transistors. And that is how an engineer is working. He is trying to make things better in terms of performance. The engineer is trying to make things better in terms of performance. So if for the same output or any expression of any Boolean expression which is related to any circuit, if it uses more number of transistors, it is not good for the overall circuit design because it will be using more resources that would consume more power. So you can see the an engineer is not only talking in terms of improvement of the transistor technology where the transistor is squeezed down. The transistor is squeezed down to achieve higher package density, higher speed, and lower power. But also in reducing the number of transistor to get the same output. So by transistor, we mean PMOS and NMOS transistors. So whenever we are talking about transistors, we are actually talking in terms of PMOS and NMOS transistor or the CMOS transistor. So everything can be translated into CMOS technology. Is that clear? Yes?
Yes, sir.
And the other very important thing is that you need to know that your PMOS transistor is actually represented by a bubble, while your NMOS is represented by no bubble. So as a simple operation from 0 to 1 or 1 to 0, when it is stepped up or stepped down, how does the inverter function? Is because of the basic properties of your PMOS and NMOS transistor. Now just let's talk of a very simple thing, that suppose if it is absolute zero or absolute VDD. So the voltage that you're giving to your gate of your PMOS and NMOS, if it is say absolute zero, so which of the two transistors will conduct and when? Which of the two transistors will conduct when the gate of M2, which is a PMOS, and M1, which is an NMOS, when will it conduct? Class? Hello? Are you able to see this?
Yes, sir. So none of them will conduct at VGS equal to 0.
None of them will.
Yes, sir. I guess.
Okay, when will it start conducting then?
So when VGS will be greater than VT voltage for NMOS, then NMOS will conduct, and when it is in negative of PMOS conductors VTH, more negative with PMOS VTH, then PMOS will conduct.
So when NMOS, let's talk about this transition state from 0 to 1. So when you have absolute zero, like this signal, and then when it goes to a high signal, so if this is your input, 0 going to 1, okay, the output should be just opposite, bang opposite, so V out should be bang opposite of this. So how would you explain the working? So when you gate voltage is at absolute zero, so you say what happens to your PMOS? What happens to your PMOS? Will it conduct or not?
So we say ki it conducts.
And your NMOS transistor
will be in cutoff at that time.
Correct? And then when there is a transition, so from 0, there is a transition. The only thing that you need to remember, the conducting state will be when it is more than your threshold voltage. As we have seen, that is why we started with the basic definition of threshold voltage, how one can control before fabrication of the chip and post fabrication of the chip. So how can you change the threshold voltage before fabrication? Yes? Manas? Manali? Sai Sudhir? Yes?
So body effect by controlling the body.
That is post fabrication. Correct. So if you have the fourth terminal, if you give the voltage, it will change the overall threshold voltage. So that is once you have, when you say post fabrication means when your chip is already ready. But you can also manipulate or get the desired voltage of your threshold voltage. That means you can increase and decrease even when you are processing the wafer or you are manufacturing the chip. So how can you do that? Samata? Sai Sudhir? Manali? We have talked at the very initial stage. What are the parameters that define your threshold voltage? Hello, Samata?
Yes, sir.
Yeah, tell me.
Yes, sir. Can you repeat the question once again, sir?
Yeah, so Manas just now told us that once the chip is fabricated, you can still change the value of or control the value or change the value of the threshold for the two transistors by giving a bias to the body, right?
Uh,
That is
yes,
post
sir.
fabrication
Yes.
when you have the chip already fabricated. But within the fabrication step, that means when you're making the chip, you can still control or change the value, and
Yes,
that
sir.
is dependent on various
Dimensions of width, length.
parameters of the transistor.
Yes, sir.
So can you just let us know what are those parameters by which you can change the value of the threshold voltage? Yes.
Yes, sir. One thing is by body effect, sir, and another one channel length modulation, sir.
Channel length modulation
I
will
mean,
change the
like
threshold
dimensions.
voltage.
Sir, I mean like dimensions of length and the width. TOX also, sir, like thickness of the metal oxide.
Channel length is not the right answer.
Yes, sir.
Yeah. So what is the right answer? What is the basic definition? What all parameters your VT? I think we did a numerical on that. Their doping concentration.
Scaling effect, sir. Yes, a scaling effect.
Huh?
By scaling effect, sir.
Scaling effects. No, scaling is just you're reducing everything. You're confusing. Can you go back to your basic knowledge? I think this has been taught to you, and there was an examination on determination of the threshold voltage. So that threshold voltage, what all parameters were there? That could be that could be applied at the fabrication of your transistor or the chip. I think you've still not been able to relate. You're giving very arbitrary answers, very radical answers. Yes, Manali, Samata, Sanya,
Yes, sir.
huh? Tell us, how can you change or manipulate or control the threshold voltage while fabricating the transistor or the chip? Okay, in other words, would doping concentration change anything? Okay, Sai Sudhir, you okay? Those were the parameters. I think you're not able to speak, but you have told all the parameters. So those parameters basically are related to what? They are related to doping concentration and other important parameters. So you can change a lot of you can change and control the threshold voltage by changing simple parameters like doping concentration or the work function. So when you're talking about work function difference, what does that mean? What metal you use? 5ms is metal semiconductor. So metal has a work function, semiconductor is silicon most of the times. So what metal you will be using, that itself can change the overall threshold voltage, and which is an important parameter to define when the transistor would be in conducting state and when the transistor is in the non-conducting state. Remember, when we are saying the transistor threshold voltage is the voltage beyond which your transistor gets into the conducting state. Okay, before or below the threshold voltage, the transistor is in the off state or the subthreshold stage, where there is still a conduction of current, but that is almost 3 or around 3 order of magnitude lower than the normal conduction. So if it is milliampere, then the subthreshold means current which is flowing below the subthreshold voltage, would be in nanoamperes. So it is very, very low. So it is almost insignificant, but it makes a lot of significance because as the number of transistors keeps going higher, as the number of transistors keep going higher, say from 10 to power 3 to 6 to 9 to 12. So now in a chip, you're having almost 10 to power 9 to 12 number of transistors. So what will happen? That value from that subthreshold current will be getting higher in order of its magnitude, because if it is 10 to power 9, if one transistor is having subthreshold current of say nanoamperes or picoamperes, so if they are 10 to power 9 or 10 to power 12 transistors in a chip, then the whole unit would be the whole unit which is having billion to 10 to power 9 to 10 to power 12 transistors, it shall have the leakage which would be formulating from each of these 10 to power 9 to 10 to power 12 transistor, which would scale up the overall leakage current from nanoamperes to amperes, or from picoamperes to amperes, because each transistor would be contributing to the subthreshold leakage. Is that clear? Hello?
Yes, sir. Yes, sir, clear.
Okay, so CMOS inverter as a switch. So please note down this one. So as a switch, when the voltage Vin is equal to VDD, so when you give an input voltage equal to VDD, which is higher than VTH to the PMOS transistor, then the PMOS transistor acts as a switch and the NMOS transistor acts as a resistor. So in this configuration, when your Vin, which is the voltage that you're giving to the gate of PMOS and NMOS transistor, if it becomes equal to VDD, the NMOS transistor is in the on state, while your PMOS transistor is in the off state. So whatever is at the load of the capacitance at the output, it would all come down to your source of your NMOS transistor. So this transistor just acts as a resistor, while this transistor, which is your PMOS, is acting as a switch. In the other case, when your Vin is equal to 0, that is the gate voltage that you're giving to your PMOS and NMOS transistor is at 0, then the PMOS transistor is acting as a resistor to the flow of current from your source of PMOS to the load capacitance CL at the output, while the NMOS transistor acts as a switch. So the NMOS transistor is in the cutoff state, while PMOS is acting as a resistor. So it will be just offering some resistance to the flow of current from VDD to your load capacitance CL at the output. And the delay that would occur would be due to the resistance and capacitance of the MOSFET transistor. So tau is equal to RC. So this is how CMOS inverter is acting as a switch, or the so-called switch model. Okay, so we have only talked about the inverter when it is at 0 state or your VDD state, which is high state, that you're giving to your, that you're offering to your that you're giving as an input to your gate of PMOS and NMOS. How about the transition state from 0 to 1? Because this is in digital form from 0 to 1 and 1 to 0. It doesn't happen without a glitch. There is a transition time for your voltage to step up from 0 to 1. So this is not exactly 90 degrees. Similarly, transition from 1 to 0, which you give as an input to your gate of PMOS and NMOS, doesn't happen without a delay. So this is basically going from 0 state to 1 state in terms of voltage with respect to time scale. So that is why we shall be also talking in terms of a concept which is called as the voltage transfer characteristics. Which we shall be seeing at a later stage. So CMOS inverter and its static behavior would constitute a high noise margin. We shall see it at a later stage, which is ideally equal to the supply voltage. That means if low voltage is defined as 0 and high voltage is defined as VDD, so the difference between 0 and VDD, suppose VDD is 5 volts, or it's 2.5 volts or 1.5 volts, then to achieve a high noise margin, ideally it should be equal to 5 volts or 2.5 volts or 1.5 volts. We shall further see that there is a range of voltage which defines 0, and there is a range of voltage which is defined as 1. And it is not absolute VDD or absolute 0. In the static behavior, we shall also talk about ratio-less logic level. So this ratio-less is actually with respect to the W by L ratio. Why it becomes very important is because of anybody in the inverter. In the inverter, the W by L of PMOS and NMOS is different. Can anybody answer me why? Manali? It has to do with the internal property of the transistor. So internal property basically means internal property of PMOS and internal property of NMOS. While designing an inverter. Samata? Sai Sudhir? Manali? You just need to see the equation, current equation, ID for PMOS and NMOS. Is there a difference, say in saturation condition? Any parameter which differentiates PMOS with respect to NMOS? Correct, correct. Mansa is right. It is mobility of the charge carriers. Correct. So, so which one has more mobility? Which one has more mobility? Which has more mobility? Is there some problem? Okay, electrons. Is there some problem with the speaker? Mansa? Since electrons are much faster, electrons are much faster than holes. So in PMOS, holes happens to be your charge carriers, while in NMOS, electrons happens to be your charge carriers. So electrons are much faster than the holes. That means the flow of electrons in your NMOS transistor would be much faster than the holes in your PMOS transistor. So how would you equate the two? It is by taking by changing W by L ratio, which is width to length ratio of PMOS with respect to NMOS. So the two currents would be same if you increase or decrease the W by L ratio of NMOS with respect to PMOS. So to what order the mobility of electron and holes are different? They are almost twice as fast. So you have to have the same current, same flow of current, you have to design the W by L ratio of NMOS and PMOS transistors, taking into account the mobilities of electrons and holes. Then in the static behavior, you need to have low output impedance so that the device or the circuit is less prone to noise. It should have high impedance. That means it should be able to have an improvement in the fan out. So we shall be defining fan out. Suppose in the steady state, this inverter is connected to your 4 other inverters. So output of inverter 1 is connected to input of 4 inverters in the next stage. So in steady state, this would be having a fan out of 4. So this is an important feature when we talk in terms of transient response. Transient response, which shall require a high impedance. And lastly, there is no static power consumption. So what does static basically means? Anybody? Manas? Manali? What does static mean? Have you done static and dynamic behavior before? Hello?
No, sir. We haven't done static and dynamic behavior.
Okay. That may be the reason. Okay, I think so. It's almost time right now. It's almost 1. I think I will stop here. We shall start with defining static and dynamic behavior so that we are able to understand no power consumption, no static power consumption. What do you mean by dynamic? So it's basically talking about transition from 0 to 1 or 1 to 0 and at the static state and as well as at the dynamic state. So it's almost 1. So let's stop it here. I have another class from 2 to 3. So I would like to end here maybe next time. We shall start from static and dynamic behavior and then we shall further be able to understand the various concepts here. Okay, any questions?
No, sir, no question.
Thank you.